Welcome everyone. In today's video, we're going to talk about rotational spectra for linear molecules. So we've already addressed the idea that the selection rules, right, the specific selection rules are that delta J can increase by 1 or decrease by 1, right? And so the only energy gap that really we care about is that energy gap between J and J plus or minus 1, right? Because again, right, for this light to be absorbed, right, your molecule, right, some of the selection rules, right, is the gross one is that it has to have a dipole moment. The specific is delta J is plus or minus 1, which then is related to the energy selection rule of the fact that your energy of your light has to match up with the energy of that transition, okay? And so in this case, right, the energy of my transition, right, is the changing energy between my initial and final state, okay? Right, the energy between J to J2 to J3 is the exact same as the energy change from J3 to J2, right? So we're just going to look at, right, transition from J to J plus 1, okay? Because again, the energy gap is the exact same type of thing, okay? Right, where the idea here is J is just the lower energy state that we're defining, okay? Right, and so, right, if we want to know the energy change from right, 4 to 3, right, it will be the same energy change as 3 to 4, okay, right, and so again, it doesn't really matter if we look from J to J minus 1 or J to J plus 1, we'll get the same energy gap, right, as long as we're talking about the transition between the two same states, right, and so here focusing on J to J plus 1, right, for a linear molecule, just plug in for J and J plus 1, okay. And you can simplify things and you'll get, right, this answer here, that the energy gap between the J and J plus 1 state is just 2 HCB times J plus 1, okay? And so this energy gap is telling us, right, this is the energy of your photons, right, of your light, right, that's shined on your object. That is the energy that your light needs to be for a transition to occur, right? Assuming you satisfy the other selection rules, right, the energy of the light that you get corresponds to that energy gap, right? So every peak you see in a rotational spectra, right, corresponds to this type of an energy gap, where the only difference between those peaks are what are the values of J for that transition, right? So here, right, in the bottom right, we have plotted some different rotational spectra for a linear molecule, okay, right? I've written out what some of the energy gaps are for some of the lowest energy transitions, right, by just doing J, starting at J equals 0, going to J equals 1, J equals 2, J equals 3, J equals 4, right? And we get, right, that this energy gap starts at 2 HCB, then increases to 4, 6, 8, 10, so on and so forth, right? And so, right, in the rotational spectra, I will get a bunch of peaks that show up, right, that correspond to 2 HCB, right, then 4, then 6, then 8, then 10, then 12, then 14, and blah, 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 right, so on and so forth, right? And so, right, each peak is at a higher energy, and each peak is 2 HCB higher than the previous peak, right? So a convenient thing to notice is that the energy gap, or the difference between any of these two peaks is always 2 HCB, right? That this difference between any two peaks, right, is 2 HCB, because we're always increasing by 2 HCB for each one of these peaks, okay? The point here, though, is for these rotational spectra, you have multiple peaks that occur because the gaps change as J changes. Okay. Right, and so we can use, right, the spectra to get information about the molecule. Often what you try to get from the information from the molecule is the bond distance between different atoms, okay? And you get that from the fact that B is proportional to the inverse of the moment of inertia, right? And that moment of inertia is related to the separation distance of your masses times the mass, right? And so let's say I have a diatomic molecule, right? Then I know what the masses are, and I can use their separations, right, to to determine what that moment of inertia is. Okay. And so yeah, so right, the rotational constant here that you get out is often used to determine geometric values and properties of your molecule. Okay. Right. So that does it for rotational absorption and emission spectra. Right, the emission spectra didn't really talk too much about, but it looks the exact same thing as the absorption. Right, it's just you kind of flip it, right? Because as you go to higher J values, right, you're going to get to lower and lower energies. Okay. In the emission spectrum. Okay. And so here, and we'll notice the plot of this rotational spectra, right? You have a variety of peak heights, okay? And you know, the overall spectra might look something more like what I've drawn in the red, and not these individual peaks, right? But this spectra is composed of individual peaks, okay? And the maximum of this spectra, right, is given roughly by this formula here, okay? And this is obtained by taking Boltzmann probability distribution, right? P is equal to e to the minus e sub j over kt, right, divided by q, right? So taking this probability distribution function, taking the derivative with respect to j and setting it equal to 0, right, and solving for j, and that gives you roughly where this maximum is at. And it comes out to be related with this formula here. Kt times, or divided by 2hcb to the 1/2 minus 1/2, okay? All right, so we can use that equation in the previous slide, right, to solve this problem, right? The equation was J max, right, is equal to Kt over 2hcb, right, to the 1/2 minus 1/2, okay? Right, and the question here is what's the most highly populated rotational level for Cl2 at 25 degrees Celsius, given some of these constants, right? And so solve for that, right, we want J max, right, so related with K, 1.38 times 10 to the minus 23, right, times the temperature, which is 298 Kelvin, right, divided by 2 times 6.626 times 10 to the minus 34, right? That's h. C is your speed of light, just 3 times 10 to the 8, roughly, I believe, meters per second. Okay. And then B, here's your rotational constant that I'm going to convert to meters. Okay. So if I have something that have units of 1 over centimeters, right, I want to convert to meters, I got to multiply it by 100 centimeters to get 1 meter. Okay. So I'm going to multiply this number by 100, okay, to get 24.4 inverse meters. Okay. And I do that so that everything's in your standard units. Okay. And when you solve for this, you'll eventually get the J max, right? And this is minus 1/2, right? When you solve for this, you get a J max is roughly equal to 20, okay? By just plugging in all of these things. And that will be it for a discussion about rotational spectra for linear molecules.